All right, here's solutions to perfect problem 6 for Math 243, hypothesis testing. So suppose I extracted a spray from elephant tusks that I claim decreases turnovers per game for point guards. All right. We know that on average a point guard will have 3.1 turnovers per game. So this is saying all point guards, we're talking about a population value right here. The population average is 3.1. We'll use the symbol mu naught for that. Mu naught equals 3.1. With the standard deviation of 1.2. So again, the standard deviation has to do with the population. This is all point guards here. So this is sigma equals 1.2. But then we get a random sample of 36 point guards. So our sample size n is 36. And the sample average was only 2.8. So x bar is 2.8. And we want to determine with 95% certainty. 95% certainty tells us that alpha is 0.05. We want to determine if my claim is true. Let's see, I claim here it is. I claim that this spray is going to decrease turnovers per game. I thought my claim wasn't in there, but it is. Claim that it decreases. All right, and I want to do the classical method, and then I want to do the p-value method, and then I want to figure out type 1 and type 2 errors. All right, let's do it. Classical method. So the first step it asks for is to state the null and alternative hypothesis. We use H0 or H naught for null and H1 for alternative. The alternative hypothesis is what my claim is, and the null hypothesis is kind of that my claim is wrong, that this spray doesn't have any effect. So mu, maybe I should write that up. Mu is the population average. Population average turnovers per game. Of all point guards. That use this spray. So not to be confused with mu naught, which is the population average of all point guards, period. Mu is the population average of all point guards that are using this spray. And then my claim is that this spray is going to decrease. So I claim that mu, this thing that I'm talking about here, will actually be less than 3.1. And it's going to decrease turnovers per game. Whereas my null hypothesis is that it's the same, that mu is just equal to 3.1. And since I say that mu is less than 3.1 here, what I have is a left-tailed test. So there we go. Under the classical method, here's my null and alternative hypotheses. These are identical for the p-value method, so I won't have to redo this. Shape, center, spread. These are also the same regardless of what method you use. So this shape, we have approximately normal. I should learn how to abbreviate that like AN or something so I don't have to write it on every single problem. Approximately normal, just like every other problem in this class. And the reason why is because our value of n is greater than or equal to 30. Talking quantitative data, and that's our criteria. N in this case was 36. 36 is greater than 30. Therefore, by the central limit theorem, we'll have this shape of approximately normal for our sampling distribution. The center, we want to use mu naught for the center, which is 3.1. And the reason we use mu naught is because when we're trying to figure out the center, it's kind of the center for mu, but we're assuming that the null hypothesis is correct, that mu equals 3.1. And the spread for our sampling distribution is sigma over the square root of n, which was, what, 1.2? Did I make these numbers work out nicely? I did. Sigma was 1.2, and 1.2 over the square root of 36 is 1.2 divided by 6, which is 0.2. Shape, center, spread. All right, and now I'm going to do what makes classical unique. So I guess this is A, this is B, And then for C, my picture in C will be different for classical than it is for p-value. Either way, I'm going to draw a distribution. I'm going to try my best to get it approximately normal. That's actually kind of a pretty one. And the center of this distribution should be 3.1. This is the x value. It'll also be handy to have the z values, so I'll write the z value below it there. And then what I want to do is create my rejection region. I want the total area of my rejection region to be 5%, and this is a left-tailed test. So I want to pick some value over here that makes all this area here 5%. So this right here is equal to 0.05. Because the total area of my rejection region, there's just one because it's a one-tailed test, is 5%. So I want to figure out what value corresponds with that, specifically what z value corresponds with that. I can use the inverse norm function on my calculator. Inverse norm always wants area below, which in this case is 0.05. And then the mean is 0 and the standard deviation is 1 because I'm talking about z values. And if you put that in, you get negative 1.645. And I'll put that down here on the z row rather than the x row because these are z values. And then what I want to do, maybe I'll change colors so this stuff doesn't run into itself too much, is talk about what my test statistic is. Figure out where, let's see, the middle was 3.1, but x bar was only 2.8. I want to figure out where the hell 2.8 is on this picture. And the way I can figure that out is if I hit stat and then tests and then z-test. I have statistics. Mu naught was 3.1, 3.1. Sigma was equal to 1.2. Again, make sure you put in sigma, not sigma sub x bar. X bar was 2.8, and n was 36. And my alternative hypothesis is that mu was less than mu naught. So I'll go down here and hit calculate, and what I get is that my z score was negative 1.5. Negative 1.5 is greater than negative 1.645. In other words, it's over here somewhere. I'm going to kind of be short on room, so I'll put it a little bit below. Negative 1.5 is not in my rejection region. This 2.8 up here corresponds with the z-score of negative 1.5, and that's not in my rejection region. So what I do is, I think I make a conclusion, calculate the test statistic, and draw my conclusion. Test statistic is negative 1.5, and my conclusion is because my test statistic of negative 1.5 is not in the rejection region, there is not sufficient evidence to reject H naught, to reject my null hypothesis. I'm not saying that my null hypothesis is right, I'm just saying there's not enough evidence to conclude that it's wrong. So because my test statistic of negative 1.5 is not in the rejection region, there's not sufficient evidence to reject H naught. What I can now do is redo this using the p-value method, but what you'll see is a lot of the work we can just reuse. Our null and alternative hypotheses, identical, exact same. Our shape, our center, our spread, identical, exact same. The first time things get different is when you get to draw your picture. I'll try to draw my picture. It'll start out looking the same, or the same-ish. We get this approximately normal distribution. We still get 3.1 is in the middle. We still get that has a z value of 0. But now I don't create rejection regions. I don't do this green step. I jump straight to this negative 2.8, or sorry, this value of 2.8, which had a test statistic of negative 1.5. So what I get is that my test statistic is right here. And if my test statistic's right there, I can figure out the area to the left of my test statistic, because this is a left-tailed test. And that area, this shaded red area right here, is called my p-value. And in this case, the p-value is equal to 0.067. So there's no rejection region at all. We just go straight to the p-value. But the idea here is that that's enough to decide if this test statistic would have been in the rejection region. Because our p-value here is larger than alpha, what that means is that our p-value is closer to the middle than our critical value right here. So if our p-value is or our test statistic is closer to the middle than our critical value, that means that our test statistic would not have been in the rejection region had we set one up here. So you don't even have to set one up. You can just kind of figure out what would have happened had you set one up. So you draw your conclusion, and what your conclusion says is because p-value is greater than alpha, because 0.067 is greater than 0.05, I have alpha somewhere here. Because the p-value is greater than alpha, and then we can jump to right here. Because the p-value is greater than alpha, there is not sufficient evidence to reject the null hypothesis. Make sure I did everything. Sketch a distribution showing the test statistic, that's this guy, and the p-value. Draw my conclusion, done. So it looks like we got everything here. And if you can start to see the conclusions between classical and p-value, you're doing really good. It takes a little while to make that make sense. The last part here are the type 1 and type 2 errors. Type 1 error is that you incorrectly reject the null hypothesis. Incorrectly reject H naught. So if you reject H naught, you're concluding that this spray works. So that is, you conclude the spray works when in fact it does not. The probability of this happening is exactly alpha. Kind of the idea here is that if it doesn't work at all, we'd expect 3.1 turnovers per game. Could we get less than whatever this value of turnovers is right here? Sure, you could. I mean, you could have the spray not working at all and just by dumb luck end up way the hell out here. What's the probability of that happening? Exactly 5%, the area of this rejection region. So the probability of a type 1 error is this 0.05, and it's incorrectly rejecting the null hypothesis, concluding the spray works when in fact it doesn't. Type 2 error. It's kind of the other way you can go wrong. So the type 2 error is you incorrectly fail to reject. So incorrectly because it still says error, but now we're failing, we're having our other conclusion, failing to reject. So if you fail to reject the null hypothesis, you don't conclude that the drug works. In other words, that is, you don't conclude that the drug works. Or the spray, I guess I shouldn't have said drug. Is that worth deleting? I guess. That the spray works. When in fact it does. You don't conclude that it works when in fact it does. So kind of two things can go wrong. Either the spray doesn't work, but you conclude that it does, or the spray does work and you conclude that it doesn't. And those are what are called type 1 and type 2 errors. And I guess that's the end of this perfect problem.